watch that video.
All right, let's go ahead and take a look at our homework. Page 199 in your textbooks. Page 199 in your textbooks. And you had numbers 2, 3, 5, 8, 9, 10. That all reviewed what we talked about yesterday with pictures and proportions. Then number 12 was just a review problem, just a review proportion. Really didn't have anything to do with geometry. It was more algebra. But 2, 3, 5, 8, 9, 10, and 12 on page 199. Have your books open, if you would, to page 199 as well. And in class yesterday, we started a page of class notes called Pictures and Proportions. And Genesis, the first picture that I had you put down was a picture of a triangle, but in the triangle, we drew a line that was to one side. So it could have gone parallel this way. It could have gone parallel this way. We chose to draw it going parallel this way. Doesn't really matter because you could always rotate the page. But we said that anytime you have a triangle in which a line is drawn, it could be here, 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 doesn't matter. As long as it's parallel to one side, there are 3 proportions in words that we need to have memorized. Ethan, give me one of them. Chris, can you help it?
Bottom to top.
Bottom is to top as?
Top is to bottom.
Nope.
Or bottom is to top.
Bottom is to top. It's very easy to remember because they're the same on both sides. Bottom is to top is bottom is to top, meaning the bottom segment is to the top segment as the other bottom segment is to its top segment. Did that jog your memory? You got another one for us. Whole is to top is whole is to top. Meaning, of the 2 sides that are being divided by the parallel, this whole side is to the top segment, as this whole side is to its top segment. And the last one, Jamie?
Whole is to bottom as whole is to bottom.
Whole is to bottom as whole is to bottom. And really, these are just, the last 2 are simply a transformation of the first one, that the whole side is to the bottom segment, as the whole side is to the bottom segment. And I said, you're going to be given 3 lengths. They could be tops, bottoms, holes, it doesn't really matter. You're going to be given 3 lengths, asked to find some 4th length. We want to start by looking at the side with the missing length. And that's what we were practicing with on numbers 2, 3, just 2 and 3. On number 2, it said that in Theorem 53, so that means we would have to flip back in our textbooks briefly to page 196 for just a moment and look at the picture of Theorem 53. The triangle was named A, B, C, and the name of the parallel was D, E. So we needed to get that lettering from the picture. So in that picture, minus all the little extra parallels, right, it says if AD is 4 inches, if DC is 6 inches, if BE is 13 inches, find EC. And of course, I told you one of the first things you want to do is label on the picture everything you know. As we look at the side with the X, Quentin, what 2 things do I have on the X side?
Well, you have the bottom.
I have a bottom and I'm trying to find a top. Okay, so which proportion should I use if there's a bottom and a top in play here? Absolutely, bottom is to top is bottom is to top. So if we start on the side with the X, we can say the 13 bottom is to X top, as 4 bottom is to 6 top. And then to solve the proportion class, of course, we will cross multiply. It being 4x is equal to 78. Divide both sides by 4, and that goes in, let's see, 1, with 9 to the 2, 19 and a half. And we got 19 and a half, and it did have inches, so I need to have inches as well. How many had 19 and a half inches? I would accept 19.5. All right, questions on that first one? Looking at the second one, number 3, same picture, because it says in Theorem 53, so same picture, but different lengths that I'm finding, different lengths that I am given. And this time it says AC is 15. So I'm going to label it this way. So I see that I'm talking about the whole thing is 15. DC is 10. It says EC is 9. And it says to find BE. So I labeled that X. Again, look at the side with the X. Audrey, what 2 things are in play on the X side? Bottom and top. So once again, we're going to use the proportion. Good. So on this side, bottom, X is to top, 9 is bottom. I don't know the bottom. Is to top 10. Well, you can find the bottom, though. You know the top is 10, the whole is 15. So what's the bottom length, class? 5. And so you cross multiply 10x equals 45, you divide both sides by the 10, you get 4.5. This time there are no units, so it's just 4.5. And then we have 4.5 for number 3. Questions on that? Use the proportion. Now, we could have said, hey, here's a hole in a top. So we could have said, well, let's find this whole side. We could have said whole is to top as whole is to top. And we would have gotten x equal to 13.5. And we could have used the 13.5 and the 9 to get the 4.5. But that's remembering an extra step in there. I don't want to have to do that. So that's why I say look to the x side to tell which of the 3 proportions we want to use. Let's take a look at number 5, and this referred to corollary 53.2. So you want to look right across the page at the top where you've got corollary 53.2. You've got a series of parallel lines here, cut by a couple of transversals that look something like this. You've got segments A, B, and C. You've got segments M, N, and R. Now there's a bunch of little dotted lines they used in the proof, but that's all we really need here. What proportion, if you will, series of ratios that are equal, goes with this picture, Genesis? It's not in words, it's just kind of an idea that we should be able to extrapolate out. Good. Anytime you've got a series of parallel lines, each segment between two lines is to the other segment that's between the same 2 lines as the next segments are to each other, as the next segments are to each other. So each one's paired up in ratio with the other segment that's between the same 2 parallels. So when it tells us that A is 12, I put a 12 there. It tells me B is 5, I put a 5 here. It tells me C is 15, I put a 15 here. It says M is 10, I put a 10 here. And it says to find N and R. Of course, you understand a proportion, in order to work it, can only have how many ratios, class? 2. So we're going to exclude the third ratio for a moment and just use my first 2 ratios. When we cross multiply, we'll get 12n is equal to 50, and you should have found n to be 4 and 1/6. How many got that length for n? And then for r, remember my recommendation from yesterday. We could put 4 and 1/6 right here, but I don't want to do that. Instead, I'm going to ignore the existence of this ratio and use these 2 in proportion. Again, cross multiply to get 12r, this time equals 150. And when we divide away the 12 goes in 1, 2, 12.5. For our r, did we get 12.5? Of course, you're welcome to use the calculator. I will typically show it without the calculator just so you can see how to work it, but certainly free to use that. Questions on corollary 53.2? Yes, sir?
Can we do some more of these?
We will do more in just a little bit, absolutely. That's a good question, good. All right, let's move on to number 5. Or,
yeah.
Or number 8.
So technically, does A have the same? So A has the same length as M?
It does not the same length. For instance, if I had a line like this length here is going to be considerably longer than this length here.
Right.
But the ratio of these 2 lengths will be the same as the ratio of those 2 lengths. Will be the same as the ratio of those 2 lengths. That's what we were showing. That's what was explained in the video lesson yesterday. Let's go and take a look at number 8 now. And Theorem 54, remember, flips the whole thing on its head. Instead of saying this line is parallel, therefore these 3 proportions are true. The Theorem 54 says if these proportions are true, then the line is parallel, right? The converse statement. So that's what was being asked here in on numbers 8, 9, and 10, I believe it was, when you were given some lengths and the question was, based on these lengths, is DE parallel? R is one of these proportions true? So let's look at what we're given in number 8. It said that AD was 3. We label it on the picture. It says that DC is 2.5. It says that BE is 4. And it says that EC is 3 and 1/3. And the question is that line a parallel? Well, notice in both cases, class, I've got what 2 things? Bottoms and tops. So I should try to plug it into the proportion. Bottom is to top as possibly bottom is to top. And to know if it's a true proportion, I should be able to cross multiply. That is, I should be able to show that the product of the means equals the product of the extremes. 2.5 times 4 gives 10. 3 times 3 1/3 gives 10. They are equal, so is the line parallel, class?
Yeah.
Yes, because based on these lengths, the sides are divided proportionally. Therefore, the line must be parallel. How many had yes for number 8? Questions on 8. Does it make sense now if we missed it?
Let's calculate on the calculator.
All right, let's go ahead and take a look at number 9. Similar problem, different information. This time we're told that AD is 1.5 feet. We are told that DC is 2 yards. We are told that BE is 18 inches. And we are told that EC is 3 feet. And the question is this line parallel? Well, obviously the problem we run into here is as we try to set up, once again, bottom is to top is bottom is to top, my units are all over the place, aren't they? Here I've got a 1.5 feet to 2 yards. Here I have 18 inches to 3 feet. Within each ratio, what has to be true of the units, class?
They have to be equal.
They gotta be the same. Now I don't have to make all 4 units the same. I just have to make these 2 that I'm trying to put in this ratio the same, and these 2 the same. I have 1.5 feet, but I've got 2 yards. How many feet are in 2 yards, class?
6.
6 feet. Now I can cancel. We can say that 1.5 is to 6, possibly as, well, I've got 18 inches and 3 feet. Well, 3 feet is how many inches, class? 36.
Why not do 18 inches?
1.5 feet. You could do that, I suppose. I'm just going to do the 18 to 36 because my calculator is going to take care of all of this work anyway. So we try to multiply 6 by 18. We try to multiply 1.5 by 36. See, this comes out to
108.
108, and this comes out to definitely not that. It comes out to like 48, it doesn't it?
Um,
Is that line going to be parallel, class?
No.
Nope. Can't be. Not if it doesn't make a true proportion. How many had no for number 9? No for number 9.
54.
I'm sorry, 54?
1.5 times to 36.
Yeah, it's 54. Still not equal, right now by a long shot. Real quick, Brecken, how we coming? You finished with the identify? All right, let me go and give you that quiz if you want to clear your desk except for a pen. Let's take a look at number 10. I believe it's the same type of problem once again, where we're given information about the triangle and asked if the line is parallel. Yes, and it is. So let me go ahead and erase this again. And this time, no units. I like it when there's no units. All right, AC, the whole thing is 12. AD is 9. EC is 2. And BE is 6. Problem is I don't have matching stuff, do I? Here I've got a hole and a bottom. Here I've got a bottom and a top. I can't put that together. So I either need to find a hole, class, which would be 8, and then I can do holes to bottoms, holes to bottom, or I need to find the top, which is 3, and then I can do bottoms to top as bottoms to top, or for that matter, I can do holes to top as holes to top now. Right? Really doesn't matter. Probably the conventional way here would probably be to find the 3. How many did? How many found the 8 for the hole instead? Let me show it both ways. So if you've got the 3, then you're probably doing bottoms to top as bottoms to top, right? 9 is to 3 as 6 is to 2. And yes, it checks out. Or if you find the hole, we've got hole is to bottom as hole is to bottom, cross multiply, get 72. Either way, the answer is yes. How many had yes? It is parallel. Question?
So if bottom is to top is bottom is to top, would the top be to bottom is top is to bottom?
Yes, that would be simply the inversion transformation, wouldn't it?
Yeah.
Yep, good question. All right, questions on that? Let's take a look at number 12 now, which had nothing to do with geometry. It says if the square root of x is to 2, as the square root of x plus 3 is to the square root of 5, solve for x. And you might have looked at that and said, oh my goodness, is that thing ugly? But that thing is begging for a transformation. What transformation is it begging for, class? There's only 5 of them.
3.
Square.
The power root transformation. Because what makes it ugly are those radicals, right? But if I were to use the power root transformation, in which you raise everything to the same power, all of a sudden now, the radicals are gone. Washington, D.C. wishes they could get that to happen. Anyway, no, the problem is Washington, D.C. doesn't want that to happen. Anyway, but yeah, just square everything. And now all of a sudden we've got what looks to be a pretty straightforward proportion, class.
5x.
Product of the extremes and the product of the means.
4x plus 1.
And we move the 4x over as a negative to get 1x equals 12. How many have 12 for your answer? Super easy if you square everything. If you don't, it's a bit of a pain. Questions on this? Questions on this? All right. Go ahead and set your books aside, set your notebooks aside. Just have some paper out. And let's go ahead and practice with those pictures I gave you yesterday and their proportions. I want to make sure we're able to work all the different, well, I say all, there's two pictures, the pictures and all of their various proportions with relative ease. All right, lesson 36, Brecken. Lesson 36. All right, if you would, go ahead and draw a triangle on your paper. And name the triangle, if you would, ABC. Any triangle on your paper, doesn't really matter. Go ahead and label it ABC. And if you would, draw a line parallel to AB. I don't care where you draw it, because we don't trust our eyes anyway. But call it MN. We are going to be given that MN is parallel to AB. We're going to be given that MN is parallel to AB. If AM is 4, if BN is 3, if CN is 5, at your seats I want you to find AC. Obviously not drawn to scale, and that's okay.
Why do you have a question mark by BN?
That's a new problem. We're working this one right now. All right, did you label your picture correctly? That's important. Did you label your picture? Check your picture, look at mine. Did you get everything labeled the same way? Which proportion should I choose? Which would be best? Ethan? There's 3 to choose from.
I did bottom top.
That's a poor choice. What should I do? Look at the side that it has the X.
Lowest to bottom.
I should do whole is to bottom as whole is to bottom. Because then I can say whole X is to bottom 4 as whole, well, what is the whole, class? 8 is to bottom 3. That's going to be your best ticket forward. You could solve this, and then if you can remember to add it to the 4, you could still get the right answer. The problem is geometry students forget to add the 4. They leave this answer, and they get it wrong. So my recommendation, because I've been doing this for 12 years now, is don't screw it up. So go with the side that has the X. When we cross multiply, 3x equals 32, we end up getting X as what, class? 10 and 2/3. And there were no units, so I don't need any units. Now, if you got 6 and 2/3, that's this length. Don't forget to add the 4 to finish it out and get 10 and 2/3. So technically, yes, you can do bottom is to top, but you better remember to add. Does that make sense? Okay. How many got the 10 and 2/3, regardless of how you did it? So you did remember to add, which is good. I know Murphy's Law says it's going to be on a quiz or test, you're going to forget it. All right, draw the same picture again, or if you wrote lightly, maybe erase. I get the luxury of erasing, but you may not, so you may need to quickly redraw the picture. Shouldn't take you real long. This time, the given information, obviously M in parallel AB, got these lengths. AC 18, CM 10, BC 12, BN question mark, because that's what we're finding. Hence the question mark in answer to the earlier question.
How do I turn into a fraction again on my calculator? I'm sorry, no, I got it. You got
got it? Okay. Yeah, it's the second bottom up on the left hand.
I did second function and then I clicked the fraction key on X instead of the reverse arrow.
All right, how many have the correct setup? What proportion are we shooting for, Audrey?
Whole is to bottom.
So start with the X side. We would write what in the proportion then?
12 is to X.
12 is to X, whole is to bottom, as 18 is to the bottom, which we don't know, but we can very easily find to be 8. All right? We cross multiply. We solve, and goodness, this is not coming out evenly. 4 would be 7.
5 and 1/3.
5 would be 90. Yeah, 5 1/3. So 5 1/3, and there were no units. So leave it at 5 1/3. How many have that? Excellent questions. All right, next one. I've got a triangle XYZ. I've got a line JK parallel to YZ. I'm not kidding. I want you to find KY given the other 3 lengths. Now for this one, you're going to have to kind of look at it sideways here. Here's the base, here's the vertex. So this would be your bottoms, your tops, and your holes, correct? Again, training your eye to kind of see it sideways. What proportion should we use this time, Genesis? Well, if you look at this as the bottom, then yes, whole is to bottom, but then this would be the, so I'm kind of looking at its base. Whole is to top is how I'd see it, but I suppose you could do whole is to this piece here, as long as, when you found the whole to be 9, you put it with the 5. Right, so we say whole is to bottom. In your case, I would say whole is to top. So you said, plug in the numbers now.
9.
Whole is to bottom. This is the whole. What is the bottom segment that you said you had? X. Whole is to its own bottom segment. Again, I look at it as a top segment. You're looking at it this way as a bottom segment. That's fine. But you better say whole is to its own bottom segment as, there we go, is to, there we go. Does that make sense? So whole would be, in your case, to bottom, as whole is to bottom. That's how we need to set it up. How many have this proportion? 12 is to X is 9 is to 5. We'll cross multiply to get the 9X equals 60 and, is that 6 2/3?
Yes.
And there were units this time, so we need to tack on the centimeters in our answer. How many have the 6 2/3 centimeters? Questions? Yes, sir.
I ended up doing both of them because at first I thought the first one I got 6 2/3 centimeters, but I also did the other one and I got 5 1/3 centimeter.
You also did the other one.
Yeah, I did 9/4.
Oh, okay, that would be wrong, wouldn't it? Because this segment does not correspond to the 4. So we have 12 and 9 are both holes.
Yeah.
They correspond to each other. X and 5 are both, in my opinion, tops. They correspond to each other. The 4 and the X do not go together. So again, we make them mirror each other. Let's do this next one. Same picture, different information. Same picture, different information. what proportion do we want this time, Jamie?
Whole is to, let me see, whole is to bottom as whole is to bottom.
Good, again, if you're looking at this as the base, whole is to bottom is whole is to bottom, right? So when we plug it in, how do we set it up?
10 is to x as 8 is to 3.
Perfect. We'll cross multiply, get 8x equals 30. We'll divide both sides by 8 to get 3 and 3/4 and inches. So 3 and 3/4 inches should have been our answer. How many have that? Do we understand how to plug these things in? Let's flip it on its head now. I've given you 4 different lengths. My question, is OP parallel? I've drawn it so it looks parallel, but we don't trust our eyes. If these are the lengths, is it actually parallel? As you set up your picture, the problem is here I've got a bottom and top, here I've got a hole and a top. That doesn't really work, does it? So I either need to find the missing bottom class, 2, or I need to find the missing hole, 7. Doesn't really matter. If you do both of them, you can now do hole is to bottom is hole is to bottom, hole is to top is hole is to top, or bottom is to top is bottom is to top. You take your pick. Probably most of us found the 2.
I did the whole.
You did the 7? All right, so if I find the 2, I would say that, let's see, 3 is to 4, the 6 corresponds with the 3, and the 2 corresponds with the 4. True proportion? No. Or if we did the 7, maybe we say that whole is to 3 top, as whole is to top. True proportion?
Nope.
No. No matter what way you do it, are you getting a true proportion? No. So is it parallel, class? No, it is not. How many had no? It is not. Your proportion did not work out. Genesis, I can't see your eyes. Question. All right. Any questions at all? All right. Now, these lines, to the best of my ability, they obviously don't look parallel at the end, but we don't trust our eyes anyway. That's the great thing about being a geometry teacher is I don't have to be a good artist because we don't trust our eyes. Those lines are parallel, and I've got 2 transversals. One transversal is cut into segments of M, N, and P. The other into segments of X, Y, and Z. I've given you lengths for 4 of the 6 segments. Find the other 2. Did you set up this proportion? Series of 3 equal ratios on your paper. 2 is to x, as n is to 5, as 4 is to 3. I cannot use the first 2 because there's 2 unknowns. I can't find those 2 unknowns. I've got to start with maybe the last 2 or the first and third. I'm going to start with the last 2. 3n equals 20, so n is 6 and 2/3. And then I'll take the first and third. 4x equals 6. And if 4x equals 6, then x is equal to 1.5. Do we get these lengths for n and for x? Questions? Yes, sir. Oh, that was a hand that you had. Any questions? All right, similar picture. We've got 4 parallel lines, 2 transversals cut into segments of AQ and Z, or AQ and X, and then ZC and R. I want you to find R, given QC, X, and Z. Did you get A is 5 1/3 and R is 1.5?
Mm-hmm.
Is that a yes, Genesis? Okay. Excellent. Any questions at all on that picture? Do we feel that we've got yesterday's pictures pretty well mastered? Okay. Want to move on to another concept then, and this is kind of a mind-blowing concept for some people. Okay. If I were to take a line, let's just call this line AB, and I were to divide the line at a point, most of you would pick some point here, maybe call it C, and then you would say there are now 2 segments to our line, correct? What are the 2 segments of my line, Genesis? AC and BC. And without, you may not have thought of it in this way, but there's now 2 segments of AB. You would go from one end point to this division point, that's one segment, and then from the other point to the division point would be your other segment, right? So that if I had a line here and we called it KM, and I were to divide it somewhere, maybe at a point we'll just call X. Well then, what are the 2 segments of KM that are formed, Audrey? KX and MX. And so when we divide a line at a point, the 2 segments go from an end point to the division point, from an end point to the division point, right? This is what's called internal division of a line. You pick a point that is between the end points and divide it internally. But you realize a line, not just a line segment, but a line can be extended indefinitely. So that because AB could be extended further, I could actually divide the line externally at a point that lies along that line. So I'd be dividing the segment AB outside the point. The reason this is mind-blowing is if you think like guillotine. If the guillotine goes above your head as you're lying there, like you don't line yourself up, then you're all right. It didn't actually divide you, okay? The problem is when it divides you internally, okay? That's just normally what we think of as dividing something, right? But because of the concept of infinite length of a line, a segment such as AB could be divided externally. The segments are now AC and BC, the same 2 segments you had before. You still would describe the segments as going from end point to division point and end point to division point. So if we were to take let me erase to give myself a better angle here. If we were to take a short little tiny line like KM, I could divide a tiny little bitty line like KM, and in geometry at least, I could divide it externally at some point X, so that my two segments are, class, KX and MX still. So that one of the segments is actually bigger than the line segment itself. That's the phenomenon that's created when you divide a line externally. You divide internally, the two segments add up to the original. When you divide a line externally, the first segment is simply the extension, and the second is actually greater than the original line itself. And that's why it can only work in a concept of infinite length. It can't work with you. I couldn't take someone like Kendall, who's not here today, and go over the top of her head, and suddenly a part of Kendall is now bigger than Kendall herself. Kendall does not extend to infinity. Far from it. Just because you actually, I would have picked on you even if you were here, Kendall. But anyway, I did think to myself, of all the days for Kendall to be out the day, I'm talking about external division of lines. It's the lesson for short people. Anyway, yeah, so the external division point actually divides into a longer segment. Yes, sir?
So why would it not be AB plus B?
Because AB is not a segment. AB is the original line. We are cutting it at point C. So the two segments, I told you this is slightly mind-blowing because we don't live in an infinite world. We don't live in an, we have a, Ethan might look infinite to Kendall, but he's not. He only goes up to 6'2" and no higher. If he were to be able to be extended indefinitely, then dividing him at some point up here would give him now two segments, AC and BC. We're going to need to tuck that thought aside as we go over two more theorems. Theorems corollary section of your notebook now. Theorems corollaries section of your notebook now. But listen to the words again as you're turning. Listen carefully. Endpoint to division point. Endpoint to division point. Because if you just look at it casually in your finite senses, you'll do exactly what Chris was thinking, and it's not correct. That's how we all would naturally think. We've got to think endpoint to wherever the division point is, that's a segment. Then the other endpoint to wherever the division point is, that's the other. Theorem 55 in your textbooks says this. The bisector of an interior angle of a triangle, the bisector of an interior angle of a triangle divides the opposite side internally. Breathe a big sigh of relief right there. We're not getting crazy on this one. The bisector of an interior angle of a triangle, the bisector of an interior angle of a triangle divides the opposite side internally into segments which have the same ratio as the other two sides. The bisector of an interior angle of a triangle divides the opposite side internally into segments which have the same ratio as the other two sides. Divides the opposite side internally into segments which have the same ratio as the other two sides. Take any triangle, bisect any angle. We'll just take the vertex angle for sake of ease. We bisect it. Now, this is not the midpoint of the base. Unless it's an isosceles triangle, this angle bisector does not go to the midpoint. There are two pieces now of my base. If I call this triangle ABC, let's just call this point P. There are two segments of the base now. There is AP and there is BP. When you compare the one to the other, that makes a ratio, AP to BP. And these two segments will have the same ratio as these two sides will have, AC to BC. That's what the theorem's saying. Let's consider the proof for just a moment. Obviously, angle bisector means you're going to have two equal angles, right? If I were to draw a line from A, and there's only one that can be drawn parallel to PC, and if I were to take BC and extend it through the point, I would get some point, let's just call it X. Well, now you realize, oh, pretend it's actually a straight extension. I didn't do a good job there. But what I basically have now is a triangle, ABX, with a line drawn parallel to one side. Bottom is to top, it's bottom is to top, hole is to top, it's hole is to top, hole is to bottom, it's hole is to bottom, right? But something else is interesting here. If this is parallel, then this angle must equal that angle because corresponding angles are equal when lines are parallel. Furthermore, this angle must be equal to this one because alternate interior angles of parallel lines are equal. And since these two angles are equal to these two angles, which are equal to each other because it's a bisector, these two angles are equal. And so if we look at this little triangle I formed on the side, it is isosceles. Equal sides, equal angles. We said before that bottom is to top, looking at this is the base, this is the vertex, bottom is to top, as bottom is to top. But remember, AC and CX are equal. And there's the proportion. That's the proof behind Theorem 55. You basically create a Theorem 53 scenario through auxiliary lines, and there it is. Pictures and proportions, page of your class notes. Pictures and proportions, page of your class notes. Draw this picture if you would. Draw a triangle. Show a bisected vertex angle. Do not make this look isosceles. Make sure one of the two sides looks bigger for your own sake. Maybe a small and a longer side. I'm going to label this as segment 1, this as segment 2. 2 segments. I'm going to label this as side 1. I'm going to label this as side 2. Notice, segment 1 and side 1 share a vertex. Notice that segment 2 and side 2 share a vertex. It would be irrational to call this segment 1 and this side 2. That doesn't make sense, does it? Segment 1, segment 2, side 1, side 2. Here's the proportion. Segment is to segment as side is to side. Write it down. Segment is to segment as side is to side. When you get a bisected angle, segment is to segment as side is to side. That's the association you've got to make. Angle bisector? Oh, segment is to segment as side is to side. It's the proportion you must memorize in conjunction with an angle bisector. Make sense? Let's see how this would play out. Let's just practice here at the board for just a moment. You'll practice tonight for homework. Okay, we've got angle bisector. Called the triangle ABC. Let's call this point P again. Suppose I knew that AC is 4. Suppose I knew that BC is 12. Suppose I know that AM is, or AP rather, is 3.5. And suppose I wanted to know BP. Anytime there's an angle bisector class, what's the proportion? Segment is to segment as side is to side. Say it with me. Segment is to segment as side is to side. One more time.
Segment is to segment as side is to side.
How will I plug in the values for segment is to segment as side is to side? Genesis? Segment is to segment. What are my segments? As side is to side. There we go. That's how we'll plug it in. We cross multiply class, we get
4x.
4x and 12 times 3.5.
42.
And divide both sides by 4 to get
10.5.
Hey, show off 10.5. Good job. So 10.5 is the length of BP.
I was
Does that make
stop
sense?
for a second.
You were letting me win that one, right?
Obviously.
All right, let me give y'all another one then. All right, let's say same picture, right? We got a angle bisector, so I know my proportion class is going to be
Segment is to segment as side is to side.
and that's not the same as bottom is top is bottom. That's parallel. Parallel is bottom is top, hole is top, hole is top, hole is to bottom, hole is to bottom. Angle bisector class is
Segment to segment, side to side.
segment is to segment, side to side. So let's suppose I now know that AP is 5. Suppose I know that BC is 8. Suppose I know that AB is 12.5, and I want to find AC. What's the proportion class?
Segment to segment as side to side.
There's just one problem. I am missing one of my segments, but I can find it easily enough. Anyone? 7.5. So how do I set up the proportion then? Audrey?
5 is to 7 as x is 8.
There we go. We cross multiply. It gets ugly, right? 7.5x equals 40. Calculators, please, because I ain't doing this in my head. 40 divided by 7.5?
5 1/3.
5 1/3.
I almost.
You almost said 5
I almost
1/3.
said
Yeah,
that.
I believe you. Just kidding.
I almost threw out a random fraction with it.
Yeah, right. 5 1/3. There's our line for AC.
And that was one number off winning the lottery.
Questions on this? All right, now, here's where we're going to apply that external division of a line, Theorem 56. Theorem 56. This is going to sound a lot like Theorem 55, but with a couple key changes. Theorem 56 says the bisector of an exterior angle of a triangle. So we're going to change the word interior to exterior here. The bisector of an exterior angle of a triangle divides the opposite side externally. So we're changing the word interior to exterior, we're changing the word internally to externally into segments which have the same ratio as the other two sides. The bisector of an exterior angle of a triangle divides the opposite side externally into segments which have the same ratio as the other two sides. Otherwise, it's word for word Theorem 55. So an exterior angle, meaning we have to extend one side to form our exterior angle. The bisector of the exterior angle, as it keeps going, is eventually going to hit the extension of AB. Here. Let's call this point P. AB is my line, just like it was last time. P is my point of division, but instead of being here, APBP, it's here, still APBP. And it's still going to be segment is to segment, as side is to side. Exact same proportion in words and everything. It's just not segments here, it's segments here and here. Do you see it? The proof would be virtually the same, except we would draw a parallel in here, call this point X, for instance, and we'd eventually show that these two pieces were equal and go from there. Not going to take time because we're running out of time, but pictures and proportions, page of your class notes. Pictures and proportions, page of your class notes. Go ahead and draw. Now, notice I made my triangle slightly obtuse. That makes it easier to extend and draw a bisected angle, okay? It's slanted, that bisected angle is going to take a long time. You're going to run out of paper. So I made a slightly obtuse angle, but it works no matter what the triangle happens to look like. It's just a lot harder to fit on a paper. Go and draw a triangle with an exterior angle being bisected. Label segment 1, segment 2. Side 1, side 2. And the proportion is still segment is to segment as side is to side. Segment is to segment as side is to side. Unfortunately, we don't have a chance to practice with this right now. We will tomorrow, and you will tonight in the homework as well. Just remember, this is not a segment. That's side 3. The segment goes from one end point to the division point, other end point to the division point. Those are your segments. Your homework, page 201. Page 201. Numbers 1, 2, 4, 5, 6. Page 201, numbers 1, 2, 4, 5, 6. We will have a quiz on Monday, not over the bisector stuff, not over segments to segment, side to side. But yes, over all the stuff we were reviewing earlier. So study over that. If you need to rewatch the lesson, you may. Obviously, Kendall hopefully was watching the lesson today. Hopefully she didn't turn it off when I started talking about exterior division points. Have a wonderful rest of your day and a wonderful weekend.